Okay, our last video here in Unit 8 is actually using logarithmic models. Um, so let's get started. There's three types of real-world problems that use logarithmic models, and that's commonly seen in earthquakes. Specifically, the Richter scale is a logarithmic scale, so it uses a logarithmic model. Sound intensity and pH level in chemistry. You may have, if you're taking chemistry, actually used logs to determine the pH given a certain hydrogen concentration, and we'll look at an example of that today. But first, let's start with the Richter scale. So on the Richter scale, each increase of 1 unit in magnitude actually represents a tenfold increase in intensity, as is measured by the seismometer. So that would mean a magnitude 2 earthquake would be 10 times as powerful in terms of intensity as a magnitude 1 earthquake. The way the magnitude works is it's actually the log of the intensity of the earthquake as measured against a threshold value, so usually given. So that would be something that's provided in the question, but if not provided, we can work around it to compare two different earthquakes. And that's actually what we're going to do in example 4. Example 4 says, how much more intense is an earthquake measuring 8.5 compared to one that measured 6.9? And the way we can do that is we can actually use the model here to compare the intensities. So let's start first with the earthquake that is measuring an 8.5 in magnitude on the Richter scale. So that would be 8.5 for magnitude equal to the log of its intensity divided by the intensity of the threshold. The threshold intensity here is not actually provided, but we'll call this first the intensity 1, so the intensity of our first earthquake. So this will be our first, and this will be our second. So the intensity of our first earthquake, that's what we want to try to isolate for here. So the way we can isolate is we can actually rewrite both sides as 10 to the power of. So we'll rewrite our left side as 10 to the power of 8.5 and our right side as 10 to the power of log base 10, which is a common property of logarithms and actually undoes the logarithm. It actually leaves us with just the intensity of our first earthquake over the threshold intensity. Why does this work? Well, another way to look at it is to rewrite this as a power. This is log base 10, so 10 to the exponent of 8.5 would equal the intensity 1 divided by the threshold intensity. Our goal here is to isolate for the intensity of the first earthquake, so we'll actually multiply both sides by the threshold intensity. So that's 10 to the exponent 8.5 times the threshold intensity. Okay, and we can do the same for the second earthquake. The second earthquake was a 6.9 on the Richter scale. So that would be equivalent to the log of its intensity. So we'll call that intensity 2 divided by the threshold intensity. And if we rewrite this as a power, that would be 10 to the exponent 6.9 is equal to the intensity 2 divided by the threshold intensity. If we multiply both sides by the threshold, we get 10 to the exponent 6.9 times the threshold intensity equals the intensity of the second earthquake. So to compare how much more intense the first earthquake was to the second earthquake, we would take the first earthquake's intensity and divide it by the second earthquake's intensity. The first earthquake's intensity was 10 to the exponent 8.5 times the threshold, and the second was 10 to the exponent 6.9 times the threshold intensity. Assuming the threshold intensities were the same, we can divide them away, and that leaves us with just 10 to the exponent 8.5 divided by 10 to the exponent 6.9. And if we do the division there in our calculators, we get 39.81. So as a conclusion, we could say the first earthquake was 39.81 times more intense than the second. Perfect. There's a practice here that you might choose to do, and then check your answer on the Moodle solution page. It's comparing, what is it comparing here? It's comparing how many times louder is a music concert with the Rolling Stones than a conversation with Mick Jagger. So there you go. And you can see the how much more intense the Rolling Stones concert would be than just a typical conversation. Our second example is actually going to be a little bit down the page, so bear with me as I scroll down here. Our second example takes us into the realm of chemistry, and it's pH. So the question says the pH scale is a measure of acidity of a substance and is based on a logarithmic scale where pH is equal to the negative log of a hydrogen concentration base 10, where H plus is the concentration of ions in moles per liter. So let's first calculate the pH of a solution with a hydrogen concentration of 2.3 times 10 to the negative 4 moles per liter. To do that, in our calculators, we just have to evaluate negative log of 2.3 times 10 to the negative 4. And that's simply something that we can type directly into our calculator and evaluate. And if you try it, we should end up with, sorry for my negative C here because I got two equal signs in the same line, it equals 3.64. So a pH of 3.64. B says the pH level of lemon juice is 2.00. What's the hydrogen ion concentration? For this one, we just work backwards. This time, given pH 2, it equals negative log of your hydrogen ion concentration. So how do we isolate for the hydrogen ion concentration? Well, we use the definition of a logarithm and we write it as a power. This is the log base 10. So 10 to the exponent of, oh, interesting, we have a negative here. If we first divide both sides by negative, we would get negative 2. So to rewrite it, 10 to the exponent negative 2 is equal to the hydrogen ion concentration. So first isolate for log by getting rid of the negative sign by dividing both sides by negative 1. And now we can use the definition of a logarithm. 10 to the exponent negative 2, not 2, is the hydrogen ion concentration. What is that? Well, if we write that as a decimal, that would be 0.01, and the units are moles per liter. That's your hydrogen ion concentration. Okay, so that's using pH and the magnitude scale. So two applications of logs.